This is Math 131, section 10.3. We talked about clock arithmetic in the previous section. Now we're going to talk about modular arithmetic. So it's kind of similar in a way. Okay. So if we talk about modulo 12 arithmetic, it's just like clock arithmetic, clock 12 arithmetic, but we do something a little different. Instead of using 1 to 12, okay, in the modulo 12 system, we replace 12 with the symbol 0. Okay, so in other words, instead of using 12 o'clock, we're going to use 0. Okay, so now we have this set of elements, 0 and then 1 through 11. So we're not going to have a 12. Okay, and then we do operation of addition. That's called a modulo 12 system, or a mod 12 system. So, and then we're going to look at smaller numbers, like modulo 5 or modulo 7 or something like that. So, but think of it this way. We always start with 0, and then we go up 1, 2, 3, 4, 5, and then we go up to, for 12, we go up to 11, because we'll have 12 things in our set, right? Because we're including 0. Okay, so it's like clock arithmetic, but instead of using 12, we're going to use 0. Okay, and that gets us to our general definition of a modulo M system. Okay, consists of M elements. Okay, and then they go 0 through M minus 1, and a binary operation. Okay, remember a binary operation could be add, subtract, multiply, divide. Okay, so let's say we're looking at like a mod 5 system, modulo 5. Then our set would have 0, 1, 2, 3, 4. Okay, we already said mod 12 was 0 and 1 through 11. A mod 7 would have 0 and then the numbers 1 to 6 in our set. And then we'd have some sort of operation like addition or whatever for a binary operation. Okay, so here's mod 7 addition or modulo 7 addition. So here's our operation, and these are the elements. Notice we have 0, 1, 2, 3, 4, 5, 6 going down, and then 0, 1, 2, 3, 4, 5, 6 going across. Now, if you get to a number that's 6 or less, it doesn't matter. You just add them, right? Like 3 plus 0 is 3. You can see 2 plus 0 is 2, 2 plus 1 is 3, 2 plus 2 is 4. But when you get past 6, okay, you're going to start over again. Okay. In other words, 6 plus 1 is not going to be 7. It's going to be 0. Okay. And 5 plus 4 is not going to be 9. It's going to be 2. Okay. So what we do is we get numbers that are in our results that are only between 0 and 6. Okay. We're not going to use 7 or 8 or 9. So if we get a number that's too big when we add, we just subtract 7. Okay. So let's say we do 6 plus 5 is 11, right? Which we can't use here, because we can only use 0 through 6. 6 plus 5 is 11. Take away 7 and you get 4. Okay. 6 plus 6 is 12. Take away 7 and you get 5. 5 plus 5 is 10. Take away 7 and you get 3. Okay. So that way we have closure. We get results that are only in the set. Now we can think of it like a clock, where our numbers on the clock are 0, 1, 2, 3, 4, 5, 6, and 0. Okay, so if we go, let's say we go 6 plus 6, we would start here to go 6 plus 1, 2, 3, 4, 5, 6. See, 6 plus 6 gives us 5. Okay, and if we look it down there, we see that 6 plus 6 gives us 5, not 12. So if you take 12 and subtract 7, you'll get that 5. Okay, or you could look at it like days of the week too, like Sunday is 0, Monday's 1, Tuesday's 2, Wednesday's 3, etc. And then Thursday 4, Friday 5, and Saturday 6. See, because there's 7 days in the week, and we have seven elements here. So you can think of it like a clock, but it only has 7 numbers on it instead of 12. Okay, now let's talk about congruence. Okay, and in referring to modulo system. Okay, so A is congruent to B modulo M. That congruence, we use that. It equals with 3 bars instead of 2. Okay, so A is congruent to B modulo M if A and B have the same remainder when we divide by M. Okay, so in other words, when we divide these two numbers, A and B, by whatever M is, we're going to get the same remainder. Okay, whatever that remainder might be, and then we can say that that's congruent. Okay, so here's some examples. 11 is congruent to 3 modulo 8. That means like when I divide 11 by 8, I'm going to get 3 as a remainder. Okay. When I divide 12 by 7, I get 5 as a remainder. So we can say 12 is congruent to 5 modulo 7. Okay. And then if I divide 5 by 3, I get 2 as a remainder. So we could say 5 is congruent to 2 modulo 3. Okay. So that's the key there, is that we want to have the same remainders. We look at the remainder when we divide. Okay. So the remainder when we divide by m gives us this number here. Okay. And that's how we define congruence. Okay. And then we develop what we call a set of modulo classes by placing all numbers with the same remainder in the same modulo class. Okay. So we kind of sort them by remainder. Okay. So when we look to a solution to a problem in modular arithmetic will always be a number from 0 through m minus 1, where m is the modulus of the system. In other words, if we're doing modulo 7, we're only going to have answers that are 0 through 6. If we're doing modulo 4, we're only going to have answers that are 0 through 3, etc. Okay, so here's an example of modulo classes. These are all numbers. We're looking at modulo 7. Remainder 0 when I have 0 or 7 or 14 or 21 or 28, etc. Any multiple of 7 divided by 7, you get a remainder of 0. Okay. For these numbers, if you divide by 7, you get a remainder of 1. See, the remainder is this number, the bold number at the top. So 1, 8, 15, 22, 29. When I divide by 7, I get a remainder of 2. That could happen with 2 or 9 or 16 or 23 or 30. And notice these are just going up by 7 every time, okay, because we're talking about modulo 7. So remainder 3 would be 3, 10, 17, 24, 31. Remainder 4 would be 4, 11, 18, 25, 32, etc. Remainder 5 would be 5, 12, 19, 26, 33. So again, if we divide any of these by 7, we'll get a remainder 5. And then remainder 6 could happen with 6 or 13 or 20 or 27 or 34. So this is how we define our modulo 7 classes. Okay, so let's look at, we're going to use modulo 7 for this example, and we're going to look at number 47. So we start by saying, okay, 47 is congruent to what modulo 7? So we divide 47 by 7, and 7 times 6 is 42. We subtract, and we get that 5 is our remainder. So we can say that 47 is congruent to 5 modulo 7. Okay, so that 5 is the remainder. Okay, you can see that remainder is coming from here, right? We just put it there. Okay, so it's just the remainder when we divide by 7 if we're talking about modulo 7. Okay, B, 86 is congruent to what modulo 7? So we're going to take 86 divided by 7, divide by 12, and our remainder is 2. So 86 is congruent to 2 modulo 7. Okay, remember, we're just looking at the remainder and we divide by 7 for modulo 7. Okay, and this should be a modulo there, not module. That should be it over there. Okay, in our last example, C, not B, 133 is congruent to what modulo 7? So we take 133 divided by 7 is 19, remainder 0. And I'll do the long division on these two. So 86 divided by 7 for B. 7 times 1 is 7, subtract. And then I bring down the 6. 7 times 2 is 14. Subtract, I get 2. So there's my remainder for that one. And if I take 133 divided by 7, take 7 times 1 is 7, right? Because I can't go to the 1. Okay. And I subtract, I get 6. And then 7 times 9 is 63. So that cancels out, right? So we're getting a 0 remainder for C for the third one, and a 2 remainder for the second one. So that's how we get our answer of 86 is congruent to 2 modulo 7. The remainder is 2 when we divide by 86 by 7. And then 133 is congruent to 0 modulo 7. We get a remainder of 0 when we divide 133 by 7. Okay, so we're always dividing by this number, by the mod number. Okay, now let's look at examples where we're subtracting. Okay, now this is a little bit different. But think about this, like 3 minus 5 is going to be a negative, right? What I can do is I can make this number bigger and still do the subtraction and get a modulo number that makes sense. Okay, in other words, I can add 7 to this 3 to make it bigger, because modulo 7, you add 7, you aren't really changing the number, right? It's still in the same modulo class. So we can make this actually be 10 minus 5 instead of 3 minus 5. And 10 minus 5 is 5. Okay, so that would be our answer, 5 modulo 7. Okay. And we can kind of do the same thing with this with C as well. See, we're going to take 5 minus something gives us 7 modulo 8. What we can do is we can make this thing bigger, okay, until we get to something equal to 7. Okay, so we can keep adding 8 to 5. So we can get 13 minus what equals 7, right? And that would be 6, right? So that gives 6 there. 13 minus 6 equals 7, right? Okay. So we can make this number bigger so we don't have to deal with negatives by adding an 8 to it. Okay, just like we made this one bigger by adding a 7. Okay. All right. Now we're going to take what minus 4 equals 3 modulo 5. Okay, that one's a little bit trickier. Okay. Now we know what minus 4 gives us 3. 7 minus 4 gives us 3, right? So we can start with that. Okay, 7 minus 4 equals 3. But we got to figure out what this is modulo 5. Okay. Okay. And we just figure that out by dividing by 5 and look at the remainder. And our remainder is 2. So that will give us 2 there. Okay. I'll just put our remainder equals 2 when we take that 7 divided by 5. Okay, so we had to do 7 because we know 7 minus 4 gives us 3, but then we know 7 can't be in this thing, so we've got to divide by 5 and look at the remainder. So we get 2 for B. So again, for part A, we have 3 minus 5 is congruent to what modulo 7? So we can take that 3 and make it bigger by adding 7 because we're talking about modulo 7, so that gives us a 10 minus 5, which gives us 5. Okay. So our answer is 5 here, and then we can say, okay, so 3 minus 5 is congruent to 5 modulo 7. Okay, and that's what our original problem was, right? We're saying this is 5 now. Okay. Okay, and for part B, what minus 4 is congruent to 3 modulo 5? So again, we can start with 7 because we know 7 minus 4 is equal to 3, right? And then say, okay, what's 7 modulo 5? Well, if I divide by 5, I get a remainder of 2. So that would give us 2 minus 4 is congruent to 3 modulo 5. Okay. And if you're not sure, you can always do the clock too. So here our clock would look like this. 0, 1, 2, 3, 4. I didn't space it out perfectly, but this is what our modulo 5 clock looks like, right? And we could say, okay, let's test it. So 2 minus 4. Okay. Now we're going to go counterclockwise for minus. So we go 2 minus 4, we go minus 1, minus 2, minus 3, minus 4. And we see we get to 3 there. Okay. Okay, and then for C, we had 5 minus what is congruent to 7 modulo 8. Okay. And we can make this bigger by adding 8. So we have 13 minus blank is congruent to 7. So 13 minus 6 is 7. Okay. So our answer would be 6 here. Okay. So we can say, to write our answer in the right form, 5 minus 6 is congruent to 7 modulo 8. Now let's do that problem, okay? Or we can say 5 minus blank gives us 7 modulo 8. So we start at 5. We're going to go backwards, right? So we're going to go 5 minus what takes us to 7. So we go minus 1, minus 2, minus 3, minus 4, minus 5, minus 6. See? So there's our answer, 6. So we can do it with a clock too. And notice my clock goes from 0 to 7. I only have 8 things on my clock. So if you draw a little clock, it's easier to do these problems too. Easier. Okay, now let's look at some multiplication problems. We're going to do 2 times what is congruent to 3 modulo 5. 3 times what is congruent to 0 modulo 6. And 3 times what is congruent to 2 modulo 6. Okay, so let's look at how we tackle these. Now 2 times something will give us something bigger than 3, right? If we do 2 times, you want to do 2 times 1, but 2 times 2 or 2 times 3. So we want to make this number bigger, okay? And we're hopefully getting something where we can get something that works. So we make this bigger by adding 5 to it. And when we add 5 to it, we 2 times what equals 8. And that will give us, in this case, 4, right? Okay. So we can actually say our answer is 4, and that's modulo 5. That works, right? Okay. And then for this one, 0 is too small. We don't want to use 3 times 0 necessarily. But we can use, we can add 6 to this, right? So if we add 6, we get 3 times blank equals 6, right? And then we can use 2 for our answer here, okay? Because 3 times 2 is 6. And that's a modulo 2 number, so that's a modulo 6 number, so that's okay. Now, the third one is a problem, okay? Because 3 times what equals 2, we want to make this bigger, so we're going to add 6 to it. 3 times what equals 8. Now, it has to go in perfectly, okay? Because we can only use those numbers. We can't have remainders or fractions or anything. So if we add 6 once, we get 8. Well, 3 times 3 is 9, right? So that doesn't work. If we add 6 again, we get 14, and 3 doesn't go into 14. And if we add 6 again, we get 20, and 3 doesn't go into 20. So this doesn't have a solution, okay? So this one, the third one, will not have a solution because we can't find a number that 3 times what equals 8, 3 times what equals 14, 3 times what equals 20 that fits perfectly. It has to fit perfectly because we're only using those numbers that we are given in our set. In this case, for modulo 6, we're only using 0 through 5. Okay, another way to do part A is to try the different ones. Try all the different elements in the set would be 0 through 4. 2 times 0 would give us 0 modulo 5. 2 times 0 is 0, right? 2 times 1 is congruent to 2 modulo 5. 2 times 2 is 4 modulo 5. 2 times 3 is 6, but remember we have to subtract 5 to make it 1, right? So 2 times 3 is equivalent to 1 modulo 5. And then finally 2 times 4 is 8. We take away 5 and get 3. So 2 times 4 is equivalent to 3 modulo 5. So there our answer is 4. So that's another way to do it, is just try all the numbers in the set. In this case, our set being, 0, 1, 2, 3, 4. So that's what we tried here. We tried all of these 0, 1, 2, 3, 4s, doing 2 times that. And then look at the modulo answer and see if we get 3, right? And we do on that one, right? So that our answer would be 4 there, okay? And again, we can do the same approach for B. So 3 times 0 is congruent to 0 modulo 6. 3 times 1 is congruent to 3 modulo 6. 3 times 2 is going to give us 0 modulo 6, because 3 times 2 is 6, and then we have to subtract 6. 3 times 3 is 9. Take away 6, you get 3. 3 times 4 is 12. Take away 6 twice, and you get 0, right? Because we can only use 0 through 5. Okay. And then 3 times 5 is 15. If we take away 6 twice, we get 3. Okay. So we actually get more than one answer here. Remember, these are the only elements we can use in the set. In modulo 6 is 0, 1, 2, 3, 4, and 5, right? Okay. So, but notice that if we're trying to get 0, that works for 0, it works for 2, and it works for 4 as well. So the answers are 0, 2, and 4. We actually have 3 answers there. Okay. And as we said before, there is no 3 times something equals 2 in modulo 6, because we're always going to get 0 or 3, so there's no solution to part C. Okay. Last thing we're going to look at here is that modular arithmetic systems under the operation of addition are commutative groups. Okay, so modular arithmetic arithmetic systems under addition are commutative groups, and we'll prove that in class. Okay, so these things that we're doing where we're adding using modular arithmetic, these are always commutative groups.